All right, hi folks, this is Larry Mussolino. I'm recording a video for STAT211. This is chapter 13, and we wanted to continue our discussion here about hypothesis testing and talk about things like p-values and forming confidence intervals and things like that. So let's get started. I want to come here to problem number 1, and this is going to ask us which of the following are true, and if it's false, explain why it's false. Let's go to part A. Part A says, a p-value of 0.01 means the null hypothesis is false. First, we should clarify, what is a p-value anyway? Well, a p-value is a probability. So remember, a p-value is always going to be a number from 0 to 1 because a probability is always a number from 0 to 1. And what the p-value is measuring is the probability of observing the sample data you did under the assumption that the null hypothesis is true. Let me give you a quick example here. Let's say Pizza Hut claims they can deliver pizzas in an average of 30 minutes. Well, maybe I do an experiment and I order 30 pizzas on 30 different days, and I find so let me write this out as a quick example here. The null hypothesis, Pizza Hut is saying their mean delivery time is 30 minutes. All right, so I collect some sample data. Maybe I collect a sample of 40 pizzas deliveries. And I find the mean delivery time, X bar, is 62 minutes. Well, the probability that the mean delivery time would be 62 minutes, assuming their delivery time average really is 30, the probability of that happening would be very, very small, right? It would be very, very unlikely for my average, for my sample of 40 pizzas to be 62-minute delivery time if the true delivery time really was an average of 30 minutes. So this would be a very low p-value. I'll say very small p-value. And if the p-value is very small, it gives us evidence to say the null hypothesis is likely not true. So we would reject the null hypothesis in this scenario, because the sample data is just giving us evidence that says the null hypothesis doesn't seem to hold water here. All right, well, the one thing I got to remember is we're basing all of this on sample data. So I can never say that the null hypothesis is absolutely false. I can't make a strong statement like that because we're just basing this on sample data. There's always a possibility that I make a mistake, an error. So my answer is going to be false. The p-value provides evidence against the null hypothesis, but it cannot prove or show that it's false. All right, let's go to part B. Part B says the p-value of 0.01 means the null hypothesis has a 0.01 chance of being true. No, that's false. The p-value isn't measuring the probability regarding the null hypothesis. The p-value is measuring the probability that you observe the sample data that you did under the assumption that the null hypothesis is true. All right, let's go to part C. Part C says a p-value of 0.01 is evidence against the null hypothesis. Well, that's true because a p-value of 0.01 would say the sample data that I observed is very, very unlikely given the null hypothesis. So that's giving evidence against the null hypothesis, right? In my example, the null hypothesis was that the mean delivery time was 30 minutes, but my sample data was 62 minutes. So the p-value might have been a number like, for example, 0.01. There's only a 0.01 chance that I would observe 62 minutes of my sample if I assume a Pizza Hut really does deliver an average of 30 minutes. So a small p-value like this is evidence against the null hypothesis. So this is true. All right, the last one. A p-value of 0.01 means we should definitely reject the null hypothesis. Well, this is false because the way a hypothesis test is set up is you have to compare. So to come to a decision for a hypothesis test, you compare the p-value to a number called alpha, Greek letter alpha. Alpha is called the significance level. And that could be different for different tests. So alpha could be, 0.08, for example. So you can't reject a p-value. You can't reject the null hypothesis just based on a p-value alone, unless you also know the value of alpha. Once you do know the value of alpha, the way you come to a decision is you say, if the p-value is less than alpha, then you reject the null hypothesis. But if the p-value turns out to be greater than alpha, then we say that you fail to reject the null hypothesis. So this is like the decision rule for hypothesis testing. You compare the p-value that's based on the sample data to alpha. Now, alpha is a number you establish at the very beginning of the hypothesis testing process. Turns out alpha is the probability of making what's called a type 1 error. And I'll talk more about that in just a minute. All right, let's go to another example here. Let's take a look here. All right, let's take a look at this. So again, let me jot down the rule. So to come to a decision for a hypothesis test, what you do is you compare the p-value to alpha. Use the Greek letter alpha like that. If the p-value is less than alpha, you reject the null hypothesis. If the p-value is greater than alpha, you fail to reject the null hypothesis. All right, this is important because this is like the decision criteria we need here. So let's go to the first part A. It says using an alpha level of 0.05, a p-value of 0.01 results in rejecting the null hypothesis. Well, let's write it down. So for part A, the p-value they're giving us is 0.01, and the value of alpha they're giving us is 0.05. Is this p-value less than alpha? Yes, it is. 0.01 is a number less than 0.05. Well, if the p-value is less than alpha, you should reject the null hypothesis. And so their statement is true. We would reject the null hypothesis. So part A is true. Let's go to part B. The alpha level depends on the sample size. No, that's not true. The alpha is set independently and doesn't depend on sample size. All right, let's go to part C. Part C says, what if the alpha level is 0.01 and you get a p-value of 0.06? Would you reject the null hypothesis? Well, let's write that down. So the p-value here for part C is 0.06, and the value of alpha they're giving us is 0.01. Well, 0.06 is a number greater than 0.01, right? 0.06 is larger than 0.01. When the p-value is greater than alpha, you fail to reject the null hypothesis. So we're going to fail to reject the null hypothesis. So their statement here about rejecting the null, that's incorrect. We're actually going to fail to reject the null hypothesis here for part C. We scroll down a little so we can come to the, right? So it says here false because a p-value less than alpha is the way you reject the null hypothesis. But in part C, the p-value was greater. So that was incorrect. All right, and let's go to the last part, part D. It says using an alpha level of 0.05, a p-value of 0.08 means the null hypothesis is true. Well, again, we can never make a statement like the null hypothesis is true. Because remember, we're only basing this on sample data. all we can say is a p-value greater than alpha only indicates there's not enough evidence to reject the null hypothesis. So this statement is false. All right, let me go to another example. All right. So it says here, suppose you're testing a hypothesis that says the null is p equal 0.23. Remember, p is the population proportion. The alternative is p not equal to 0.23. You took a sample size of 350 and you ended up with a sample proportion. We write that as p hat. The sample proportion is 0.29. Come up with a 95% confidence interval. Well, what I'd like to do here is kind of avoid a messy calculation. What I'd like to do instead is let StatCrunch do the work for me. So here's what I'm going to do. Let me bring up StatCrunch here side by side if I can. So I'm going to bring up StatCrunch here. And if you remember, for this kind of a test, we want to go to Stat, Proportion Stats, one sample with summary. And this is the same command you use for confidence intervals or hypothesis testing. All right, so I'm going to do it. Let me go to StatCrunch. I'm going to go to Stat, Proportion Stats, one sample with summary. I come up to this input screen. Now, I know the number of observations is 350 because that's the sample size. But I also need to know the number of successes. Now, the number of successes isn't given to us in this problem, but we can calculate it. To find the number of successes, what we can do is say, all right, 29% of the sample, let's say, responded yes to a survey question. If 29% responded yes out of 350 people, then what that must tell me, I'm going to just multiply 0.29 times 350, and I'm getting 101.5. So what it means is 101.5 people said they responded yes. Now, I know I can't have 0.5 of a person, but I'm going to enter 101.5 in this input box. And I'm going to come down here to confidence level. And this problem said come up with a 95% confidence interval. So I'm going to leave this at 0.95. I'm going to click compute. And here is the confidence interval that we're looking for. Let me scroll over a little bit. So if you notice here, the lower limit of the confidence interval is 0.242. Here it is, 0.242. The upper limit is 0.338. Here it is. Now it says come up with a conclusion for the hypothesis test, but using this confidence interval. Well, we just came up with a statement that we're 95% confident that the population proportion is in this interval of 0.242 to 0.338. But we're trying to test the null hypothesis that says p equals 0.23. You notice p equals 0.23 is not contained in this interval. So that means we can say we're highly confident that p equals 0.23 is not the population proportion. So that means we could say the confidence interval doesn't contain the null hypothesis. So we can reject the null hypothesis here. All right, let me go. Let's do one more example here, maybe. Yeah, let's take a look at this one. So in this example, they're going to ask us about what's called type 1 and type 2 error. So let's discuss what that is first. Well, you know, when you're conducting a hypothesis test, you could make a mistake. You could make an error. Because remember, you're basing this on sample data. So it's always possible that you come to an incorrect conclusion. And there's two ways you can make a mistake. There's something called the type 1 error. Type 1 error. And this happens when you reject the null hypothesis, but it was actually true when it was actually true. So of course you made a mistake. You shouldn't have rejected the null hypothesis because it was actually true, but you did reject it. So that's the error you're making. What about a type 2 error? Well, type 2 error is kind of the flip of this scenario. Here you don't reject the null hypothesis. When it was actually false. So you should have rejected the null, but you didn't. That's the error you're making. All right, so let's take a look at a couple of these examples. Let's go to part A. It says the null hypothesis is p equals 0.2 versus p less than 0.2. And later it's discovered that p is 0.3. So the question here is, should we reject or fail to reject the null hypothesis? And did we make the right decision or did we make an error? Well, if p is equal to 0.3, the alternative is saying that p is less than 0.2, which it's not. So really, we should fail to reject the null hypothesis. And that's what we did. So we should have failed to reject, and that's what we did. So we didn't make a mistake at all. So no error occurred on this one because we correctly did not reject the null hypothesis, and that's what we should have done. Now you got to keep in mind that what they're saying to you here is later on you discover the true value of the population proportion. Well, that's unusual that you would really know that, but we're assuming that for this question. Let's go to part B. Let me erase some of this to, let's go to part B. Part B says you do a hypothesis test where the null is p equals 0.7 and the alternative is p not equal, and you rejected the null hypothesis. Later, it was discovered that p equals 0.85. Well, here we should have rejected the null, right? The null was saying that p equals 0.7, but we found p significantly different. So we should reject the null. And that's what we did. We did reject the null. So we did what we should have. So again, there's no error here. So no error occurred on this one because the null hypothesis was rejected and that was the right decision. That's what we should have done. All right, let me scroll down here a little bit and we'll go to part C. We scroll down here to part C. All right, let's take a look at part C. Part C says you're doing a test where the null is p equal 0.6. The alternative is p less than 0.6, and we failed to reject the null. Later, we discover that p equals 0.5. Well, we did not reject the null here, so part C, we did not reject the null. But what should we have done? Well, if p is equal to 0.5, we should reject the null, right? Because this is saying the alternative is p less than 0.6. But if p is actually equal to 0.5, then this is going to be a type 2 error, right? The null hypothesis should have been rejected, but we did not. So we did not reject the null hypothesis when it was actually false. Well, that's the definition of a type 2 error. So part C is a type 2 error. The null hypothesis should have been rejected, but we didn't. All right, let's go to part D, the last part. It says the null is mu equals 25. Remember, mu is the population mean. And the alternative is the mean is greater than 25, and you reject the null. Later, you discover that mu is 24.9. Well, for this one, we should not be rejecting the null hypothesis, right? Because really the alternative is saying that mu greater than 25, but it's not. It's 24.9. So we should not, so for part D, we should not reject, but we did. So we rejected, but but the null was true. Well, that's the definition of a type 1 error. So the answer on this one is type 1 error occurred because the null hypothesis should not have been rejected, but we did reject it. That's the error that we just made. All right, folks, hope this is helpful as you're working in the chapter 13 homework.